Now we will have a small revision about spherical mirrors.
Hi friends, do you know that mirrors are of different types? Plane mirror and curved or spherical mirrors. Spherical mirrors can be further divided into concave mirror and convex mirror. So there are three types of mirrors: plane, concave and convex. In fact, I have all these three mirrors on this wall here for you. I'm going to go and stand in front of each of these mirrors and let's see what do we observe. If I stand in front of the first mirror, I appear to be the same height. If I stand in front of the second mirror, oops, I appear to be inverted. Now if I move close to the mirror, I appear to be magnified. Now if I stand in front of the third mirror, I appear to be shorter. Can you guess the type of mirror for each of these? That's right. The first mirror is a plane mirror. The second mirror is a concave mirror. And the third mirror is a convex mirror. Let's talk about the three mirrors. A plane mirror has a plane or flat surface. And I'm sure you must have noticed that when you stand in front of a plane mirror, you appear to be the same height. Now let's look at concave and convex mirrors. These mirrors are curved mirrors. And a very simple way to understand them is using a spoon. So I'd like you to pause the video right here and go and get a spoon. And it'll be great if you can get a large and shiny spoon. So are you ready with your spoon? A concave mirror is curved inwards. So if you look at this side of the spoon, can you see it is curved inwards just like a concave mirror? Now hold the spoon like this and look at yourself in the spoon. What do you observe? You appear to be inverted and smaller in size or diminished. Now if you bring the spoon really close to yourself, you can see that you are looking magnified. But an easier way to do this is to hold an object like a pencil and get it really close to the mirror. Now you can clearly see the magnification. So a concave mirror is the only mirror that can produce an inverted image in this position or a magnified image. A convex mirror is the opposite of a concave mirror. So if we flip the spoon, here we have a convex mirror. Now if you look at yourself on the convex side of the spoon, what do you notice? You appear to be smaller, but your image is now straight or upright. And no matter where you move the spoon, the image in a convex mirror is always diminished and upright. So this was our quick recap on the three mirrors. More details on spherical mirrors coming up later in the video. But first let me ask you, which types of mirrors are you using in your daily lives? I'm using all three types of mirrors every day. If you don't believe me, I'll be showing you some clippings from my daily life. And you need to be a detective and identify the type of mirror. Is it a plane mirror, concave mirror, or a convex mirror? Are you ready? Let's start. In the morning, when I shave, which type of mirror am I using? The shaving mirror is a concave mirror. The face in the mirror is magnified. If I flip this mirror, there's a plane mirror behind this. Can you see the difference in magnification between the plane mirror and the concave mirror? When I comb my hair, which type of mirror am I using? This mirror has a flat surface. It's a plane mirror. When I leave the house and go down in the elevator, which mirror does the elevator have? It's a plane mirror. To save time, I can actually comb my hair on the way down. While driving the car, I use the two mirrors. the rear view mirror and the side mirror. Which types of mirrors are these two mirrors? That's right. The rear view mirror and the side mirror are examples of convex mirrors because they give a greater field of view. There are mirrors kept at road intersections so that you can see the vehicles coming from the other side. Which type of mirror are these? That's right, convex mirrors. So as you can see, I'm using all three types of mirrors every day: plane, concave and convex mirrors. Concave and convex mirrors are together called spherical mirrors. Now, do you know why they are called spherical mirrors? If I take this ball, it has the shape of a sphere. Now let's imagine the surface of this ball to be shiny like a mirror. I wish I had a silver colored ball, then it would actually look like a mirror. Now if I take this knife and I cut the ball here, this slice is a curved mirror. It's called a spherical mirror since it's come from a sphere. If the inside portion is polished, it's called a concave mirror. If you polish the outside portion, it's called a convex mirror. An easy way to remember the concave mirror is, it's as if you're entering a cave. It's a hollow portion. So this side is a concave mirror, and the opposite side, which is bulging, is a convex mirror. The concave mirror can be represented by this simple diagram, where the smooth side is the shiny reflecting surface. The side with these small dashed lines is the back of the mirror. Similarly, for the convex mirror, the smooth side is the shiny reflecting surface, and this side is the back of the mirror. Now an interesting question is, why these mirrors behave differently? To understand, let's imagine we are throwing a parallel beam of light on all the three mirrors. Let's start with the plane mirror. So if you throw the parallel beam of light, can you see that the light rays remain parallel even after reflection? Next, let's try the concave mirror. Now if you throw the parallel beam of light, can you see that the concave mirror converges the light rays to a point? The concave mirror is a converging mirror. And now let's look at the convex mirror. So if you throw the parallel beam again, can you see that the convex mirror is diverging the light rays? So the convex mirror has a diverging action. It's a diverging mirror. Here's a comparison table of a plane, concave and convex mirror. Now you must be thinking, why curved mirrors converge and diverge light rays, but a plane mirror does not? Is it because these laws of reflection hold only for a plane mirror and not for curved or spherical mirrors? What do you think? The answer is, the laws of reflection always hold for both plane and curved mirrors. Let's take a closer look. So if you draw the normals at each of the points of incidence for the light rays, the angle of incidence is always equal to the angle of reflection. But the concave and convex mirror have a converging and diverging action because of their curved shape. It's due to their curvature that the light rays reflect in this manner. There are some important terms for spherical mirrors. For example, pole, focus, center of curvature, principal axis, and so on. Let's understand these terms with the help of a simple diagram. Let's start with the concave mirror. The center of curvature is the center of the hollow sphere of which the mirror is a part. The center of curvature is represented by C. The center of the surface of the concave mirror is called the pole, represented by P here. Radius of curvature R is the radius of this sphere. The straight line passing through the center of curvature and the pole is called the principal axis. The portion of the mirror where the reflection of light takes place is called the aperture of the mirror, represented by mm dash here. Remember, the concave mirror is a converging mirror. If a beam of light that is parallel to the principal axis is incident on the concave mirror, after reflection, the rays meet at a point on the principal axis. This point is called the focus, represented by F. The focus is exactly in the center of P and C. The focal length F is the distance between the pole and the focus. So focal length equals radius of curvature by 2. Now let's take a look at the convex mirror. Center of curvature is the center of the hollow sphere of which the mirror is a part, represented by C here. Note that the center of curvature of a convex mirror lies behind the mirror. The center of the surface of a convex mirror is called the pole, represented by P here. Radius of curvature R is the radius of this sphere. The straight line passing through the center of curvature and pole is called the principal axis. The portion of the mirror where the reflection of light takes place is called the aperture, represented by mm dash here. Remember, the convex mirror is a diverging mirror. If a beam of light that is parallel to the principal axis is incident on the convex mirror, after reflection, the rays appear to diverge from a point on the principal axis. This point is called the focus, represented by F. The convex mirror has a virtual focus, since the focus lies behind the mirror. The focus is exactly in the center of P and C. The focal length F is the distance between the pole and the focus. So focal length equals radius of curvature by 2. Let's place the label diagram of a concave and convex mirror on our concept board.
See, this is a bottle with water. Now, I'm inserting my pencil into this water. So, can you see? This pencil which is inside the water appears big. Why this is? This is called as refraction in science. This is another one property of light. So what is refraction? When the light goes from one medium to another medium, the path of the light changes. This is called refraction. Why the path of light changes? The reason is, when the light goes from one medium to another medium, the velocity of light changes. Because of that, the path of the light changes. See here, in this diagram, air, water is there. Light goes from one medium to another medium, that is air to water medium. If there is no water medium, the path of the light will be like this. See here, this is an incident ray, falls on the surface of another medium and get refraction and goes like this. This is called refracted ray and this is called incident ray. Now we are going to draw a normal at the point of incidence. Now we can see the incident ray, the normal and the refracted ray all lie in a same plane. Now this is the incident ray and this is the normal ray. The angle between the incident ray and the normal ray is called as angle of incidence. It is denoted by the letter I. This is normal and this is refracted ray. The angle between the normal and the refracted ray is known as angle of refraction. It is denoted by the letter R. This is the original path of the light if there is no medium, and this is the refracted ray. The angle between the original path and the refracted ray is known as angle of deviation. It is denoted by the letter D. Now we are going to the second law of refraction. The ratio of sine of angle of incidence to the sine of angle of refraction is a constant. It's called as refractive index. This refractive index is denoted by the letter mu.
What can happen when a beam of light is incident on the surface of any object? When a light beam is incident on the surface of any object, a part of the light can be reflected by the object, a part of the light can be transmitted. That is, it may pass through the object and get out from the other side, and a part of the light can also be absorbed by the object. The amount of light reflected, absorbed or transmitted depends on the material that the object is made up of. If an object is opaque, then it will absorb and or reflect most of the light back. If it's transparent, more light will be transmitted. Can you think of examples for these two? The surface of a mirror is shiny and opaque, and most of the light rays are reflected from it. On the other hand, glass is an example of a transparent object. It will transmit most of the light. So what is refraction of light? Here's how we define it in simple words. It's simply bending of light when it travels from one medium to another. Yes, if it is incident at this angle, then it goes through at another angle. Now this is not the exact definition, as there are a few technicalities involved. Let me explain it to you. Consider a transparent object kept here, say a glass slab. Suppose light travelling through air is incident obliquely on the surface of the glass. What do I mean when I say obliquely? It means slant. It implies that the incident ray is neither parallel nor at a right angle to a specified line. Now this light will bend at the boundary of the two media. Here, the two media are air and glass. This bending of light at the boundary of the two media is what we call refraction of light. We see that at this point, the light bends. It's not going straight. What are these two mediums called? The medium from where the light is incident is called the incident medium, and the medium where refraction occurs is called a refractive medium. Similarly here as well, the light is travelling from one medium to another medium. It's from glass to air. And here also it is incident at an angle. Since we know that air is a transparent medium, light bends at this boundary and travels through air. So light refracted at these 2 points. Let us draw a line perpendicular to the surface at this point of incidence. This line is also called a normal. What is this angle called? It's called the angle of incidence and is denoted by the letter I. It is an angle made by the incident ray with the normal. And this is the angle made by the refracted ray with the normal. It's called the angle of refraction R.
Now we will discuss about the path of the refracted ray. See, first diagram. Light travels from air medium to water medium. Air is optically rarer medium and water is optically denser medium. When the light goes from optically rarer medium to optically denser medium, the refracted rays goes towards the normal. Now, in this diagram, the light travels from water medium, which is optically denser medium, to air medium, which is optically rarer medium. When the light goes from water to air, it moves away from the normal. Now, in this diagram, light goes from air to water through the normal. When it goes from air to water through the normal, there is no deviation, there is no refraction, it goes straight.
In the previous part of this lesson, we saw what refraction of light is. It's simply the bending of light when it travels from one medium to another. The question I left you with was, why does light change its direction after entering another medium at an angle? Let's discuss that in detail. The change in direction of light occurs because of the change in the speed of light in that medium. When light enters another medium, there is a change in its speed. The speed may either increase or decrease depending on the medium. Note that when we say that the speed will increase, it does not mean that the speed will be greater than this value, which is the speed of light in vacuum. When the light is entering into the glass at an angle, it travels at a lesser speed than in air, and when it goes from glass to air, its speed increases. So it's because of this change in speed that the direction of light changes. But what if the light is entering perpendicular to the surface of the glass? Will its speed change? Yes, its speed will change, however, it does not bend this time. Yes, the refracted ray propagates in the same direction as the incident ray. Talking about the case when light enters at an angle, There is one more observation that we can make. Observe this part of the refraction. Observe the incident and refracted rays. We notice that the refracted ray is more towards the normal than the incident ray. When the light rays enter the glass from air, it bends, and it bends towards the normal. And from this refraction, we can see that when the light ray again enters the air, it bends away from the normal. So we can say that when the light travels from an optically rarer medium to an optically denser medium, it bends towards the normal. And when the light travels from an optically denser medium to an optically rarer medium, it bends away from the normal. What do we mean by optically rarer and denser mediums, by the way? An optical medium is a medium through which light can propagate. Since both air and glass are transparent, light can pass through them. So, both of them are optical mediums. What about rarer and denser? If the refractive medium is optically rarer compared to the incident medium, then the speed of light in it will be greater. And when the refractive medium is optically denser compared to the incident medium, the speed of light in it will be lesser. Note that in both cases, we are comparing the speed of light with the speed of light in the incident medium. So what do we understand by this? How can we summarize it? When light is traveling from an optically rarer medium to an optically denser medium, its speed will decrease and it will bend towards the normal. Whereas when the light is traveling from an optically denser medium to an optically rarer medium, its speed will increase and it will bend away from the normal. Now that this is clear, I want you to understand another concept. Now, instead of a glass slab, we have water, and also suppose that the ray of light is incident in the same direction. We can see that this angle is the same in both the cases. So will the refracted ray in this case travel in this direction only? In other words, will the angle of refraction be the same in both cases? No, the angle of refraction will be different in this case. In fact, the angle of refraction here is greater than the previous one. So what can we infer? We can say that the refraction of a light ray depends on the material medium on which light is incident. Yes, light rays will be refracted by different amounts in different materials.
Now we are going to talk about the topic total internal reflection. It is another one property of light. We know very well when light travels from optically denser medium to optically rarer medium, it moves away. Now let us consider an incident ray, that is AO, which travels in water to air medium. So water is a denser medium and air is a rarer medium. So when it travels from water to air, it moves away. Normal. So the ray AO is an incident ray and this ray is a refracted ray. Now you increase the angle of incidence. Now the angle of incidence is BON dash. We increase the angle. Because of that, what happened? The light ray, that is refracted ray, it moves more away from the normal. This is here. At a particular angle, that is CON dash, angle CON dash, when the light rays goes from water medium to air medium, it doesn't goes into the air medium. It goes in between the surface of air medium and water medium. Further you increase the angle, that is now the angle is DON dash. This incident ray DO, when it goes from water medium to air medium, it is not getting refracted. It is again reflected back to the water medium. This phenomenon is called as total internal reflection. Now let us see what are the conditions for the total internal reflection. Light should go from optically denser medium to rarer medium. That is the first condition. For example, it should go from water to air. Second thing, the angle of incidence should be greater than the critical angle. These are the two conditions for total internal reflection. So what are the examples for total internal reflection? Sparkling of diamond, Mirage. Next one is optical fiber. Now we are going to discuss about Mirage and optical fiber.
Hi, I'm Mr. Oh Mingyo. Okay, I'm going to discuss what is critical angle as well as total internal refraction. Okay, but before that, right, let's look at what happens when the angle of incidence is increased when the light ray is moving from air to water. Okay, from a less dense medium to a denser medium. This is what will happen if I have light ray 1. It's going to bend towards the normal. So 1 will go to 1. Okay, now light ray 2, if I increase the angle of incidence here, then it's going to bend towards the normal again. So if I have to increase the angle of incidence such that it is almost touching the air and water boundary, this is what will happen. The refracted ray is going to bend towards the normal. Okay, so when the light ray is moving from an optically less dense medium to an optically denser medium, right, basically it's just normal refraction that will happen. Okay, so now if the light ray is moving from water to air, okay, let's do the same thing again. I have light ray 1 entering into water, and when it emerges from air, it's going to bend away from normal. Okay, so 1 will go to 1, and if I increase the angle of incidence, 2 is going to go to 2, and if I increase the angle of incidence some more, 3 will go to 3. Okay, so now as you can see at this angle of incidence for 3, right, the refracted ray is almost touching the air and water boundary. So what if I increase the angle of incidence to 4? This is what will happen. The refracted ray is going to bend down further, and then it's going to touch the air and water boundary. Okay, so 4 is a very special angle, because at this very special angle of incidence, the refracted ray is moving along the air and water boundary, and it has an angle of refraction of 90 degrees. Okay, and for this 4, right, this angle of incidence, we call it the critical angle. And what if I increase the angle of incidence some more beyond the critical angle? The light ray is going to get reflected like a mirror. Okay, so this phenomenon at 5, right, we call it the total internal reflection. Okay, now let's do a recap. Okay, when the light ray is passing from a denser medium, we observe that as we increase the angle of incidence, the angle of refraction will increase slowly. Okay, and eventually the angle of refraction will become 90, and that is when the light ray will just go through the two medium separation. Okay, and this special angle of incidence, right, we call it the critical angle C. Okay, at this point, as we continue to increase the angle of incidence, the light will be reflected to the denser medium, and the refraction does not occur anymore. And this phenomenon, we term it as a total internal reflection. Okay, okay, now let's do a summary. There's altogether 3 scenarios when the light ray is moving from an optically denser to a less dense medium. When the angle of incidence is smaller than the critical angle, normal refraction will occur. That means the light ray will emerge to the other medium and get refracted. Okay, when you slowly increase the angle of incidence such that it becomes the critical angle, the light ray is now going to go through the surface boundary. Okay, and you have an angle of refraction of 90 degrees. And if you were to increase the angle of incidence even further, right, this is what will happen. Total internal refraction will occur. Okay, so these are the 3 scenarios that are possible when a light ray is moving from an optically denser to a less dense medium.
Now we are going to see the example for total internal reflection. One of the example is Mirage. In summer, we can see some water on the road. This is not actually real, this is an illusion. In summer, the air near the ground becomes hotter than the air at higher levels. Hotter air is less dense and has smaller refractive index than the cooler air. Thus, a ray of light bends away from the normal and undergoes total internal reflection. Total internal reflection is the main cause for the twinkling of stars.
Mirage. It is an optical illusion observed in deserts on a hot day. The object, such as a tree, appears inverted, and the observer gets the impression as if the inverted image has been formed by a pool of water. This phenomenon is known as mirage. Due to intense heat, the surface of Earth becomes quite hot, and the temperature of air near the surface of Earth is maximum. The temperature of the other layers of the air goes on decreasing as one goes up. Therefore, density as well as refractive index of the air increases slightly for higher layers. Thus, a ray of light traveling from point O of a tree passes through air of gradually decreasing refractive index and gets refracted more and more away from the normal. Thereby, the angle of incidence goes on increasing. At a layer, when the angle of incidence becomes greater than the critical angle, total internal reflection takes place. The ray of light starts traversing through layers of increasing refractive indices and goes on bending more and more towards the normal. Ultimately, when the ray reaches the eye of the observer, it appears to be coming from the point I. Hence, the inverted image of the tree produces the impression of reflection from a pool of water. A similar effect is caused on coal-tarred roads on hot summer afternoons when you see the inverted images of the vehicles moving ahead.
Now we are going to see another example for total internal reflection, that is optical fibers. Optical fibers are bundle of high quality composite glass or quartz fibers. Each fiber consists of a core and cladding. The refractive index of the material of the core is higher than that of the cladding. Optical fibers work on the phenomenon of total internal reflection. When a signal in the form of light is directed at the end of the fiber in a suitable angle, it undergoes repeated total internal reflection along the length of fiber and finally comes to an other end. Optical fibers are extensively used for transmitting audio and video signal through long distances. Moreover, due to the flexible nature, optical fibers enable physicians to look and work inside the body through tiny incisions without having to perform surgery.